So I hope you can hear me now.
Great. Yeah, go ahead.
Okay, thank you. So first, I would like to thank you for the opportunity to present my contents to the ISEG Society. So today I would like to present the content and the results of my investigation program on an old landfill on which household waste was deposited. In this context, the gas formation potential and the gas collection of this site was examined with regards to optimization potentials. This was a clay pit an der Holtbrücke in Bochum, which was filled with about 700,000 cubic meters of household waste between 1966 and 1976. Here you can see historical pictures of the site showing how the household waste was deposited. The dumping was done without sorting in the sense of modern waste management. Some of this dumped household waste had a high organic content. Among other things, this was kitchen garden waste such as banana peels or coffee grounds. These organic materials are decomposed by bacteria within a landfill and lead to the formation of landfill gas. In areas near the surface where oxygen can penetrate, aerobic bacteria degrade the organic matter mainly to carbon dioxide and water. In deeper oxygen-free sections, anaerobic bacteria degrade the organic matter to form carbon dioxide and methane. The landfill gas formed in this way can be emitted from the landfill body into the atmosphere and the landfill surface. In order to prevent these emissions of these greenhouse gases, gas collection was carried out at the study site by means of 6 gas wells, which are sucked in by a suction engine. A gas well is a filtered pipe inserted vertically into the landfill to which a negative pressure is applied. This negative pressure sucks the landfill gas out of the landfill in a controlled manner and currently dilutes it with atmospheric air to a maximum methane concentration of 2% and emits it. After visualization inspection of the installed equipment, the gas formation potential of the landfill body was analyzed by 3 different investigation methods. First, the influence of the suction intensity of the gas wells on the microbial degradation of the organic components of the landfill was tested by interval measurements. Before the investigation began, the landfill was heavily oversuctioned. This means that significantly more gas was sucked out of the landfill than was produced by the microbial degradation. As a result, atmospheric air was sucked into the landfill body via the landfill surface. It was assumed that a low level of suction could reduce the influx of atmospheric air into the landfill body and consequently induce predominantly anaerobic degradation of the organic matter, which also leads to increased methane production. The measurements were carried out over 10 months with a suction volume of 7 cubic meters per hour per gas well. The measurements show an increase in methane concentration from initial about 8 to 10 volume percent to about 30 to 40% by volume at the end of the measurement period. The interval measurements proved that low suction of the gas wells could produce an energetically usable landfill gas at the study site. A landfill gas is considered usable for energy purpose if it has a methane concentration of at least 40% by volume methane. Furthermore, the gas flow within the gas well was investigated by depth zonal measurements. The aim was to test whether a constant negative pressure can generate a constant gas flow over the depth. It was assumed that deeper lying deposition horizons experienced a stronger compaction due to a higher surcharge, so that they have a lower gas pathway than horizons near the surface. The measurements confirm this theory. From the wellhead to a depth about 5 to 7 meters, a clear reduction of the gas flow was detected. At greater depth, no or only a small gas flow could be detected. Oxygen was also measured in sections near the surface, indicating a strong influx of atmospheric air. The depth journal measurements confirmed that the landfill horizons were a reduced pathway with increasing depth. Suctioning the existing low suction volume only induces a gas flow in the uppermost 5 to 7 meters. In order to induce a gas flow in deeper deposits, the gas flow is reduced. To create a gas flow in deeper sections, a higher negative pressure is required. However, this higher negative pressure would also cause a stronger influx of atmospheric air in the existing gas wells, which would dilute the landfill gas more. The lean gas produced in this way could not be used for energy utilization. In order to prevent this influx of atmospheric air, it is necessary to seal the gas wells using a foaming process. I will explain this in a moment. In addition, multi-level sensor measurements were taken to determine how large the effective volume of a gas well is. For this purpose, negative pressure measurements were carried out in a landfill close to a site gas well. The results were presented in a 3D model and show that only a volume of about 2,000 cubic meters is actively sucked up by a gas well. Consequently, all 6 gas wells suck only about 2% of the total landfill inventory. The multi-level sensor investigation show that only a marginal part of the landfill is currently being actively vacuumed. Accordingly, additional gas wells can be sucked without having a negative impact on the existing gas wells. As already mentioned, in order to produce undiluted landfill gas, it is necessary to prevent atmospheric air from entering the gas wells. For this purpose, the gas wells should be sealed down to a depth of between 5 to 7 meters by means of a foaming process. In this process, the wedge section to be treated is first delimited with a lower and the upper plug. Then a 2-component foam is filled into the section between the closures. This foam expands by a factor about 12 and reaches an expansion pressure of up to 10 megapascal. Due to the expansions, the foam presses through the filter section into the surrounding filter gravel and seals it gas tight. Finally, the well pipe is mold-free in this section and now has the characteristics of a solid pipe. When this sealed gas well is subsequently sucked, atmospheric air can no longer enter, and the landfill gas is extracted from deep landfill horizons. Accordingly, a methane-rich, undiluted landfill gas is produced. Finally, the emission of a carbon dioxide equivalents resulting from the gas extraction at this site were balanced against the emission of the gas extraction with energetic gas utilization. In this calculation, the theoretic that was result from the production of the same amount of electricity and heat by conventional generation were taken in account as emissions savings based on the German electricity mix. This balancing shows that the current emissions of the gas capture of over 5,000 tons CO2 equivalents can be completely saved. Due to low suction and the energetic utilization of the landfill gas, theoretically, emission-neutral gas collection can be achieved at the study site if the generated electricity and the waste heat are fully utilized. So, thank you for your attention.